Alright, hello everyone. I hope you guys are doing great. So today we'll be attempting this Leetcode Biweekly contest 95. Right? Uh, I'll be I'll be thinking out loud while I'll be thinking the solutions, and yeah, I'll try to be as fast as possible, but I'll also try to convey my thoughts in a as efficient a way as possible. Right? Alright, so the contest has started. Let's check out the problems. Hmm. Okay, so there is some criteria. Given 4 integers representing the dimension of a box, return a string representing the category of the box. So the box is bulky if any of the dimensions of the box is greater than 10 to the 4, or the volume of the box is greater than 10 to the 9. Okay, so if the mass of the box is this, then it's heavy. Okay, so there is a bunch of if else conditions that we need to implement. So let's just do this, right? Cool. Let's just have a look at the constraints to avoid any kind of overflow. So length, width, height is 10 to the 5. Okay, so let's just find out the volume. So volume is length into width into height, right? So the first condition is if the volume is greater than 10 to the 9, right? So if volume, is it strictly greater than or equal to? Okay, so if volume is greater than or equals to 10 to the power 9, or any dimension of the box is greater than or equal to 10 to the 4. So we'll just use the maximum dimension and mass, right? Okay, so length, width and height. So if the maximum is greater than or equal to 10 raised to the power 4, then we will return bulky, right? Okay, makes sense. Mass is greater than or equals to 100, then it's heavy. So if mass is greater than or equals to 100, then we return heavy. Okay, if box is both bulky and heavy, then its category is both. Okay, damn it. Alright, so we can't simply return. So let's just look at all the other conditions. If the box is neither bulky nor heavy, so we need two variables, bulky and heavy, right? So bool bulky heavy. So bulky equal to heavy equal to false. So if this condition is true, then we'll say that the box is bulky. So we'll just say that bulky equal to true, and here we'll say that heavy equal to true. Okay, so if the box is both bulky and heavy, then its category is both. So if bulky and heavy, then we'll return both. So we can just return both. Alright, next, if the box is neither bulky nor heavy, then it is neither. Okay, so if it is not bulky and it is not heavy, then we'll return neither. Okay, bulky and not heavy. Okay, cool. So if bulky, return bulky, otherwise you can return heavy. Looks good, right? We calculated the volume correctly. Yeah, I think everything seems good. Okay, in C++ we can't take the max of 3 numbers. Alright, we use the example test cases and run it, getting heavy and neither. Is it correct? Looks correct. Let's just check it one more time. Both, neither, bulky, heavy. 1 2 3 4 5 6 7 8 9. Yeah, looks good. Let's submit this. Wow, so we're getting a runtime error here. Yeah, this should be long. So volume equals to long volume into height. Okay, should be good now. Heavy and neither. Let's submit this. Wow, again runtime error. That seems... What exactly is going on here? Long volume is... this seems okay to me. L into B into H. Well, still don't know why I was getting an overflow there, and I hope that I won't get an overflow now. Length, width, height. What's going on here? So this was weird. Anyways, let's move on from this. So for a stream of integers, implement a data structure that checks if the last k integers passed in the stream are equal to value. Okay, so data stream class initializes the object with an empty integer stream and two integer values, value and k. Boolean consec in num adds num to the stream of numbers. Return true if the last k integers are equal to val and false otherwise. If they are less than k integers, the condition does not hold true, so you need to return false. Okay, makes sense. The value of k is large. Okay, so what we can do here is we can maintain the count of the last number and what the last number is, right? So we can maintain these two values, right? So we'll have two variables. One will be count of the last number, which is initially 0, and we have a variable last number which is equal to -1. Okay, so when we get this function, then we'll simply say that count is equal to 0. Okay, so we also need k, right? So we'll have a variable val k, and we also have value. Okay, so maybe we don't need to initialize anything here. Okay, so we'll say count is equal to 0, last num is equal to -1, val k is equal to k, and value is equal to value. Or maybe we can replace val k with just k. Cool. So now we have this, we just need to implement this. So what we'll do is we'll check if this number num is equal to the last number or not, and with that we can update our count. Okay, so first we'll check if num equal to last num. If this is the case, then you will increment count. Otherwise, what you'll do is you'll set count equal to 1. So otherwise you're going to set count equal to 1. Just a moment. So we can set count equal to 1 and the last number as num. Okay, and what we need to return is we need to return true if count is greater than or equal to k. So we can simply return count greater than or equal to k. Right. Yeah, hope this works. Null true 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 true. What's the expected output? Null false false true false. Okay, what's going on here? So the input is first we insert 4 3 and then 4 4 4 3. Okay, so value and k, value equal to value. Oh, so count is greater than equals to k and last num is equal to value. This is what we need to check, right? Cool, let's try to run this now. Null false 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 false. Okay, now what's going on here? Count is equal to 0, last num is -1. Return true if the last k integers are equal to value. Yeah, adds num to the stream, right? Yeah, so first we'll check if num is equal to last num. If that's the case, then we simply need to increment count. Otherwise we'll set count equal to 1 and last num equal to num. Yeah, should be good, I guess. Okay, let's try to output count and last num, both these values. See what's going on here. Yeah, so 1 4 2 4 3 4 and 1 3 and what is k? This is actually very weird. K and value are getting some garbage value. I'm still amazed by the syntactical errors I make. Although I still don't know why we can simply not use k equal to k and value equal to value. Seems weird to me. Anyways. Okay, moving on to problem C. So here we have a zero index array nums, and the effective value of three indices I, j, k is defined as the bitwise OR of nums I and nums j, and the bitwise AND with nums k. Okay. The Xor-Beauty of the array is the Xoring of the effective values of all the possible triplets of indices. Wow, nice, nice, nice. Return the Xor-Beauty. Okay, this seems interesting. So let's try to solve this problem in a bitwise fashion, starting from the bit number 0 going to the maximum bit, which will be bit number 29. And we need to find the number of triplets such that that particular bit is set in this expression. Okay, now for a bit to be set in a triplet, the condition is that that bit should be set in at least nums k. So that's the necessary condition, that the bit should be necessarily set in nums k, and it should also be set in at least one of nums I and nums j. So k can take any value among the numbers which have that particular bit as set. And for I and j, what we can do is, out of the remaining n minus 1 numbers, we will select. So yeah, so we don't have any conditions such that I is less than j, right? Yeah. So out of the remaining n numbers, because no number will be taken out since there is no extra condition, so we'll need at least one number which has that bit set. And you know, oh, just a moment. So the Xor-Beauty, yeah, so we need one number which has that bit set, and the other number can be anything. Okay, so the number of triplets in which this bit will be set can be found out pretty easily. Now what we need to do is, we need to find the Xor-Beauty. So we need the Xor of all the triplets, right? Yeah, okay, so we need the number of triplets in which this bit will be set, and we need the number of triplets in which this bit will be not set. Okay, and then what we need is, we simply need the parity of the number of triplets in which this bit will be set. So if there are odd number of triplets in which this bit is set, then the bit will be set in the final Xor as well, right? Yeah, okay, so we just need the parity. Cool. So let's initialize some variables. N is equals to a dot size, and let's just quickly try to find out the counts of all the bits, right? There can be up to 29 bits, so we just try to find out this function. So from 0 to I is equals to 0, I is less than n, I plus plus. So for all the bits from 0 to n minus 1, we'll try to find out the count of that particular bit, right? So if that bit is active in a of I, this is the syntax to check it, then we'll say count of j plus plus, right? Cool. So this way we can find out the counts of all the bits. Now what we need to do is, we need to find the parity of the number of triplets in which a particular bit is set. So again, let's iterate on all the bits, right? And also let's initialize our answer. So we iterate on all the bits from 0 to n minus 1, and now we need to find out the number of triplets. So for j, we need a number which has that bit set, right? Okay, so int parity equals to, initially the parity is 0, right? So let's just say that initially we don't have anything. Now what we can do is, we can basically say that for k we can choose any number which has that bit set. So we can initialize parity by the count of this bit, right? So parity is count of j modulo 2, right? And now what? Now for I and j, first of all, we need at least one number in I and j to have the bit set, and the number of ways to do that would be n square minus choosing I and j such that none of them have that bit set, right? Okay, so the thing which we need to multiply here is that, so the expression that we need to multiply is n square minus number of ways in which both of them don't have that bit set, which will be n minus count j multiplied by n minus count j. Right, so this is what we want here. Since we are dealing with integers, I don't really want to go into longs. So let's try to find out a way to figure out the parity of this expression. Okay. So this n square, let's call the parity of n square as p1. So p1 is equal to n mod 2 into n mod 2, right? N mod 2 multiplied by n mod 2. Okay, and let's call the parity of this expression as p2. So int p2 is equal to n minus count of j mod 2 multiplied by itself. Although we don't really need to multiply it by itself because the parity will stay the same. So let's just keep it like this. So let's call the combination of the subtraction of them as p3. So p3 is equals to p1 minus p2 mod 2 plus 2 mod 2. And then we can say, we can just multiply parity with p2. So parity is equal to parity into p2. And now if the parity is odd, then we will add this to our answer. Finally, we can simply return answer. Yeah, okay, so this makes sense, right? Okay, let's try to submit this. So we are getting 5 here, which is the expected output. Let's run both the test cases just to be sure. 5 and 34. So this should work. Let's submit this. So we're getting a wrong answer here. Why is that? So there is just one triplet, right? This shouldn't happen. If we look at the first bit, then count of the first bit will be equal to 1. So we initialize parity with 1, and p1 would be again 1. What will be p2? P2 will be 0. So damn it, this should be p3 instead of p2. What am I even doing? Okay, so I'm taking in a lot of unnecessary penalties here, but nevertheless. Okay, now let's go to the last problem. So here we are given a 0 indexed integer array stations of length n. Stations of I represents the number of power stations in the ith city. Each power station can provide power to every city in a fixed range. In other words, the range denoted by R. Then a power station city I can provide power to all cities such that their distance is less than or equal to R. Okay, makes sense. So the power of a city is the total number of power stations it is being provided power from. Okay, so the government has sanctioned building K more power stations, each of which can be built in any city and have the same range as the pre-existing ones. What does this statement mean? Given two integers, R is fixed for every station. Okay, so this range is fixed. Okay, return the maximum possible minimum power of a city if the additional power stations are built optimally. Note that you can build the K power stations in multiple cities. Makes sense. Number of power stations in the ith city. Okay, so what this means is, let's try to see what this problem is saying. So in this problem, what we have is, we have this array, right, and the number of station a city receives power from is actually equal to the sum of all the elements in this range from I minus r to I plus r. Okay, so this is the this is the actual value of the number of stations a city receives power from, right? Yeah. Now what we need to do is, we need to install k stations somewhere, and we need to try to find out the minimum value of the maximum power that all the stations will receive, right? Maximum possible. Okay, so we need to return the maximum possible minimum power of a city. What does this mean? So the minimum power of a city is 5, and we need to maximize this. Okay. So we need to maximize the minimum power received by any city. Okay, so this is a typical example of a problem which is known as a minimax problem or a maxi-min problem, something like that. So what we need to do is, we need to maximize the minimum value of an expression. So what we can do is, we can try to use some kind of binary search. Okay, and in the binary search, what we'll do is, we'll see whether or not it's possible to build the stations in such a way that every city receives greater than or equal to x power. That is, every city receives power from greater than or equal to x stations. So initially we know how many cities a city is, how many stations a city is receiving power from. We can find that out very easily using prefix sums. Yeah, so we can find that out very easily using the prefix sums, the sum from here to here and subtracting this value from here, or we don't even need to do that. Yeah, so we'll subtract we'll just have the prefix sum from L to R, from I plus R to I minus R, and using that we can find out the initial value of the number of stations from which a particular city is receiving power. And now for all cities we know this value. So let's say this is the array of val of I, which denotes the number of cities that the ith city is receiving power from. Okay, now what? Now let's say for some index I, we realize that val of I is smaller than x. So we will need at least x minus val of I more stations. We'll need at least x minus val of I more stations to give power to the ith city. And we already know that all the cities from 0 to I minus 1 have already received this much power. So the optimal thing to do here would be to install a station at exactly this value, which is I plus R. So if we install a station here at I plus R, this will help the maximum number of people possible. So this will help the maximum number of cities possible. Right, since we iterate from 0 to I minus 1, we know that all the cities from 0 to I minus 1 already have their conditions met. So it's beneficial for us to install a station as right as possible. So we'll just install this station here. Okay, cool. Then what? We need to update the values of val I respectively, which is equal to addition on a range. That's the value of k here. K is very large, which is good for us. So we need to install x minus val of I stations in the city number I plus R. But at the same time, we need to update the values of val of I for all i's in this range. Now how do we do that? So we can keep track of all the stations that we are installing, first of all. So there is a very easy segment tree or Fenwick tree based method, but I don't really want to use some of those data structures. When we are at I, we are always installing a station at I plus R, right? Okay, so here is the observation that I'm talking about. So what we can do here is, so let's say for some future value j, we want to find out its updated value val of j. So what do we do then? What we do exactly there is that uh, all the extra values that we added when we were in this range from j to j minus r, only they need to be considered. So we can maintain a sliding window of the previous r values that we added, and we can just maintain their sum and then add it to val of j to get the updated value, right? I hope I am making some sense, right? So we can implement this now. Okay, cool. Okay, not even that. Just a moment. Not just r, I think the length of this range should be 2r, right? So when we are at I, we add stations to I plus r, right? And it will impact all the stations, the value of j of all stations till I plus r plus r. So let's say this is I plus 2r. Okay, so all of them will be affected. Yeah, so instead of r, we need to maintain a sliding window of length 2r. So we will just maintain the sum of all the extra stations that we are adding for all the indices from I minus 1 to I minus 2r, and we'll add it to our answer to get the updated value. Make sense, right? Cool. So let's implement this. So let's initialize some variables. So n will be stations dot size, and first let's build the prefix sums. Let's copy this vector to another vector of long, so we can simply avoid all the integer overflow issues. So we create another vector. We'll say ai is equal to stations of I minus 1, and p sum of I is equal to p sum of I minus 1 plus ai. Cool. Now let's build the actual val vector, which creates the which stores the value of the number of station a city receives power from. Okay. Let's define the right bounds and the left bounds. So right bound is minimum of n and I plus r, and left bound is maximum of 1 and I minus r. And what we want is val of I is simply going to be p sum of r minus p sum of L minus 1. So now we are ready to apply binary search. We need to maximize the minimum power, right? So it's always possible to have a minimum power of greater than or equal to 0. Am I right? So yeah, L can be initialized to be -1 and R can be 1e18, right? So in binary search, what we do is we simply maintain these invariants that L is always good and R is always false. R is always bad. That is, it is always possible to have a minimum power of this expression L, and it is always bad to have a minimum power of R. So I am initializing L by -1 because it is always possible to have the minimum power equal to -1. Minimum power greater than -1, greater than or equal to. Okay, cool. So mid is going to be L plus R by 2. And now we'll check if it is possible to utilize at most k extra stations and be done with it, right? So let's initialize the variable extra to be equal to 0, or maybe we can maintain a vector. So this stores the number of extra pieces that we add. Okay, and we'll also maintain the sum of the last 2R pieces that we added, and we'll try to maintain this sum in a sliding window kind of fashion. Okay. So we have an expression val here which denotes the updated value of val. So initially it is val of I, and we'll add something. So what will be adding here, right? So we know that we are maintaining the sum from what do we say? So let's assume that when we are at I, we are maintaining the sum from I. So from I minus 2R to I. Plus 2R will be impacted. Yeah. So we need this range. So let's assume that initially the sum contains the value from I to I minus 2R. Okay, so we'll say val here plus equal to sum, and we'll later on update this value. Now if val here is less than mid, so we want every value to be greater than or equal to mid, right? So we'll say that extra of I is equal to mid minus val here. Right, and now we need to update this value of sum, right? Cool. So sum initially contains the sum of values in the range from I minus 2R to I minus 1, right? Cool. So now we want this to contain values from I minus 2R plus 1 to I. Yeah. So how can we do this? We need to subtract something and we need to add something. So first of all, if I is strictly smaller than 2R, then we don't need to do anything because the window size is smaller than 2R. Now if I is equal to 2R, then what happens? So we have this value and I is equal to 2R. So I minus 2R is just 0. So we are maintaining sum from 0 to, and then we maintain the sum from so when we switch to I is equal to 2R plus 1, what happens? In this case we need the sum of sum from 1 to 2R, right? So we still don't do anything. So if I is less than equal to 2R, you don't do anything. Otherwise what you need to do is, if this is your array and this is the index where you are on, currently you have the window, currently you have the sum of these elements, and now you want the sum of these elements, right? And this is nothing but I minus 2R. So you can say that sum minus equal to extra of I minus 2R and sum plus equal to extra of I. Cool. And now we need the total number of things that we are adding extra. So let's maintain dot extra. right? Okay, so we can say that dot extra plus equal to extra of I. So we are good if extra is less than or equal to k dot extra. So if this is the case, then we'll say L equals to mid, else we'll say R is equal to mid, and finally we'll be returning L. Hopefully this makes sense. P sum R, P sum L minus 1. Okay, so val here is less than mid, then extra is equals to mid minus val here. Yeah, we can't simply continue. I think we also need to add sum plus equals to extra of I, obviously. Okay, and then we'll subtract the sum of I minus 2R. Okay, let's see. Let's try to get rid of all the compilation errors first. What's this? No match to this operator. Oh yeah. Okay, let's see. Okay, let's rename it to capital R. Wherever have we used small r? Let's see. Here, right? I don't think we've used small r anywhere else. Yeah. So we're getting 5 here, which seems to be correct. Let's use all the example test cases. We're getting 5 and 4. Okay, seems to be correct. Can we submit this? Okay, let's submit this. Integer overflow. Come on, man. I haven't even used ints anywhere. That just sucks. Line 39. What happens there? Anyways, can this dot extra value ever be... Oh yeah, it can, right? Yeah, it can very well overflow. That makes sense. Okay, let's try to submit now. Alright, so this works and we are done with the contest, but I'm pretty sure that our rank is going to be really, really bad thanks to a lot of penalties that I always end up getting somehow in Leetcode contests. Where are we? Wow, we are doing really bad. So this is probably it.